The ratio test is another sort of comparison test, only instead of comparing a series with another series, we're just going to compare terms within the same series. It's really a pretty easy test to use, and it's very, very helpful when you have series that have quickly growing functions like factorials, like exponentials, those kind of things. So when you have these functions or these terms that will grow very, very quickly, then this is when the ratio test is most helpful. All right, so let's look at it. Let the sum of a sub n be a series with non-zero terms. Then we have two cases, well, technically three, but the first case is if the limit of a sub n plus 1 over a sub n, the absolute value of that is less than 1. A sub n plus 1, we've seen that before. That's just where we take a term and then we also use the next term. So that was what that is. It converges absolutely if that limit is less than 1. That should make sense. If the limit of this quotient is less than 1, that means that a sub n plus 1 is smaller than a sub n itself. And so the function's decreasing, each and every term gets smaller. And so that's what that's telling you. Number 2 says it will diverge, the series will diverge if a sub n plus 1 over a sub n is greater than 1, and that's the opposite of what happened in number 1, and so that's telling me that a sub n plus 1 is in fact getting bigger than a sub n. So, that all just kind of makes common sense. The note is telling us that the ratio test is inconclusive. If the limit equals 1, they're growing at the same rate. And so you would need, or the terms are the same, my apologies, it's not growing or decreasing, but they're the same. You just would use a different test in this case. There's nothing really to do with the ratio test if you end up getting equals 1. All right, so example 1, determine the convergence or divergence of the series from 0 to infinity of 2 to the n over n factorial. So here we have two very fast growing terms, 2 to the n, exponential, n factorial. So this is a perfect setup for the ratio test. So we just need to determine what a sub n is, and that is, of course, the function. A sub n is the series itself, and then a sub n plus 1. We just plug in n plus 1 for every n, so that would be 2 to the n plus 1 over n plus 1 factorial. Okay. Let's get this up just a little bit. So now we want to take the limit, so the limit as n goes to infinity, and you can write it as a compound fraction, so that would be, and the n plus 1 goes on top, the second term goes on top, so 2 to the n plus 1 over n plus 1 factorial over 2 to the n over n factorial. Now that is gross, it's really big, takes up a lot of room, so it is perfectly acceptable for you to write it, instead of as a fraction of two fractions, to write it as the first term times the reciprocal of the second term. So we'd have 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n, and hopefully you've picked up on the fact that I left off the absolute value. So we do want to have that absolute value symbol, since we're coming back up here when we're done and we're going to compare it to 1. Negative 3 is less than 1, but that would not have the right conclusion if we then said it converged. So we want to be careful with that. So make sure you have your absolute values. All right, so now we want to simplify this, and so this is kind of an interesting and fun, I think, simplification process. So 2 to the n plus 1 is just 2 to the n times 2 over n plus 1 factorial. And we want to compare n plus 1 factorial with n. And so I'm going to write n plus 1 factorial as n plus 1 times n factorial, because you know how factorial works. 3 factorial equals 3 times 2 times 1. So n factorial would be n times n minus 1 times n minus 2, blah, 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 right? So n plus 1 factorial is going to be n plus 1 times n minus 1, blah, blah, blah. Well, all of this is just n factorial. So we can write n plus 1 factorial as n plus 1 times n factorial. And the nice thing about that is that that's going to end up canceling out with the n factorial over here on this side. So the n factorials cancel, the 2 to the n's cancel, and so we are left with the limit as n goes to infinity of 2 over n plus 1 absolute value. Since our n's are all positive, this will end up being positive, so that's going to end up being, the limit of 2 over infinity plus 1, which is 0. 0 is definitely less than 1, and so therefore I'm just going to call this S sub n since I'm out of room. Therefore S sub n converges, and you could say converges absolutely by the ratio test. It's pretty easy. That's all there is to it. All right, let's look at another example. Let's do this one in a different color. All right, so determine the convergence or divergence of the series from 0 to infinity of n squared 4 to the n plus 1 over 5 to the n. So this is another one where we have very quickly growing terms, these are exponentials, and we have 4 on top, 5 on the bottom, but we have different exponents, plus we have that n squared. So this is one that could be, a little difficult to kind of figure out just looking at it and reasoning through. So since these terms will be positive, we can use this ratio test. So a sub n is going to be n squared 4 to the n plus 1 over 5 to the n, and a to the n plus 1 will be n plus 1 squared 4 to the n plus 1 plus 1, so that's going to be to the n plus 2 over 5 to the n plus 1. All right, so then we're going to take the limit as n goes to infinity, and I'm going to go ahead and write it as the multiplication problem, n plus 1 squared 4 to the n plus 2 over 5 to the n plus 1 times, and be careful if you do this, make sure you take the reciprocal of a sub n. So this will be 5 to the n over n squared 4 to the n plus 1. Okay, and then when we simplify these terms out, then what we'll get is this 5 to the n plus 1 is 5 to the n times 5, and so the 5 to the n plus 1s will cancel. The 4 to the n plus 2 is 4 to the n times 4 squared, whereas this one over here is 4 to the n times just 4. So we'll actually have the 4 to the n's divide out, and then we'll have one of the 4's divide out. So we're going to end up with a 4 on top. We're also going to end up with the n plus 1 squared and the n squared, because those will not simplify out. So we're going to end up with 4 to the n plus, not to the, but times the n plus 1 squared over n squared. And even if we FOILed out that n plus 1, it's not going to cancel with the n squared on the bottom. So, but that's okay, because what we've got is, oh, I left off my 5. Silly me. There's a 5 on the bottom. Okay, I had that 5 left. Okay, so then what we've got is the limit as this goes to infinity. They have the same power. N squared and n squared. They're the highest exponents in top and bottom. So we know that this is going to go to 4/5. 4/5 is less than 1. Therefore, the series converges. And again, you could say absolutely by the ratio test. Okay, pretty fun. I like that. I like the algebra in it. I think that kind of gives a little extra fun there. All right, one more example here. So now we've got the series from 1 to infinity of n plus 2 factorial over 4 to the n. All right, they're both positive, so we're going to go ahead and use the nth term test. So a sub n is n plus 2 factorial, 4 to the n, and a sub n plus 1, is n plus 1 plus 2 factorial. Oh, not squared. Over 4 to the n plus 1. And so that's just going to be n plus 3 factorial over 4 to the n plus 1. All right, the limit as n goes to infinity of the absolute value of n plus 3 factorial over 4 to the n plus 1 times 4 to the n over n plus 2 factorial. Being careful to take the reciprocal of that second term there, the a sub n. All right, so we know that the 4 to the n's will cancel and leave us with 1, 4 on the bottom. And n plus 3 factorial is n plus 3 times n plus 2 factorial, and those will cancel out. So we're going to have n plus 3 over 4. And that, as n goes to infinity, is in fact infinity, and therefore, which is of course greater than 1. So therefore, the series of n plus 2 factorial over 4 to the n diverges by the ratio test. And there you have it. Have fun with this homework.